Yeah, so in this program we will find the way we will plot the wave function for the low, lowest four eigenstates. We will plot the probability distribution, and we will find the eigenvalues for the lowest four energy states for a particle trapped in 1D box by the FDM, that is the finite difference method. So first of all, we will be defining the variables such as L, X, H cut, or you can say H bar, M, that is the mass of electron, X over the range of 0 to L in with the difference of capital L by 98, N is equals to 100, N is the number of interval, and D is the line space, XLN. It means that a capital X, which is the 0, is the initial value, capital L, which is 10 nanometers, is the final value, and N is the number of digits in between them. So line space generally means that we can have 100. If we choose N is equals to 100, we can have 100 digits in between X and L, including these two as well. Okay, so we have and then next I have defined capital X. Capital X is the step size, and I have determined the step size by d2 minus d1. That means in this line space, the second value of this whole command minus the first value of this whole command will be my step size. So moving on to determine the eigenvalues and wave functions through this program. So I have to construct the kinetic energy matrix as well as potential energy matrix. So first of all, I need to get the matrix like this, in which the diagonal elements are 2 and the elements above and below the diagonal elements should be -1. So to construct that matrix, what I did, first of all, I created an identity matrix of n-1 to n-1. So for example, if we take n is equals to 5, so then this command means that it will create me an identity matrix of 4 by 4. So I got the identity matrix of 4 by 4. So I will multiply it with -2. You can multiply with -2 or 2. That's another thing. So, but our whole point will be to eliminate the negative sign in the diagonal. The negative sign shouldn't be in the diagonal elements. So if you are multiplying -2 here, so you have to use minus sign here also to eliminate that. If we are using 2 here, then you don't need this sign here. Instead, you will write -1 instead of 1 in these two. Okay, so moving on. Yeah, so I have created the identity matrix and multiplied it with -2. So and then I want the elements below and above the diagonal elements as 1. Okay, 1 or -1, that doesn't matter a lot. So the logic should be clear. So so I use for loop here to do that. So for I is equals to 1 to n-2. So again, if I have n is equals, for example, if I have n is equals to 5, then for I is equals to 1, I can have 1 and 1 plus 1, 2. So in the first row and second column, I will be having the value as 1, and another one I plus 1 and 1. So I plus 1. So if I take I as 1, so 1 plus 1 2 and 1. So in the second row and first column, so this element should be 1, and so on so on, this will go away. So why I take n minus 2 and not n minus 1? So there is a simple logic behind it. See, if I choose as n is equals to, and if I choose n as 5 and I have chosen n minus 1 instead of n minus 2, so I can have values from 1 to 4, right? So if I take I as 4, so I 4 and I 5. So fourth row and fifth column. So this thing doesn't exist here. So it don't have any such meaning. So if I take n is equals to 2 here, then I can have I is equals to 1, 2, 3. So in this manner, if I is equals to 3 here, so I can take as third row and 3 plus 1, 4. So third row and fourth column. So here is third row and fourth column. So this is minus 1 or 1. And again here, this is 4 and this is third. And again I have minus. Now in the same manner, if you have chosen n is equals to 100, then this loop will go for 1 to 98, so that the elements above the diagonal and below the diagonal can have their values. If you want to take minus 1, you can take minus 1. If you want to take 1, you can take 1. Just make sure that negative sign shouldn't be in the diagonal element. It should be in the above and below the diagonal elements. So by constructing this matrix, I have to multiply this whole matrix with a with this vector, that is the h cut square upon 2m s square, where m is the mass of electron, h cut is the h upon 2y, or you can say you can call it hy, and x is the step size. And I will end my for loop here. So so now our kinetic energy matrix is developed. So for potential energy matrix, in this particular case, we have taken potential energy matrix as 0. So I will be defining the 0 matrix n minus 1, n minus 1. Make sure the the order of the kinetic energy and potential energy matrix should be same. Otherwise, it will give you error. And now the Hamiltonian matrix, that is, you can also say that total energy matrix is I have denoted this with H. You can denote it with your choice of variable. So I have added both the kinetic energy and potential energy matrices. Okay. So after doing that, what I need to do is to find the eigenvalues and eigenvectors. Why? Because the eigenvalues will give me the energy values, and eigenvectors will give me the wave function. Okay, so again I have used this command called known as spec. Spec is used to find out the eigenvalues and eigenvectors of the matrices. So this is the syntax of to find the eigenvalues and eigenvectors of a particular matrices. So here F symbolizes the eigenvectors and E symbolizes a diagonal matrix in which the diagonal elements are the eigenvalues, and spec H is the eigenvalues. Okay, so I have to plot the eigenvalues as well as the eigenvectors, right? So let's start with the eigenvalues. So I have to plot lowest for, so that's why the for loop I have used, because we have n is equals to 100. So it will give me 99 eigenvalues, but I need only 4. So I will so what I will do, I will be creating another for loop in which I will define m is equals to 1 to 4, so that I can plot only 4 eigenvalues. So here I define another quantity q is equals to spec h m. M is the number of the m is the this number which gives me the eigenvalue for n is equals to 1, for n is equals to 2, 3, and 4. Here is the print command to print those values. And since we have to plot these values, so I will use plot. I will use x by L. X by L is I have divided this by L for normalization. Normalization means creating the normalizing, or you can say scaling the values from in between 0 to 1, and q is divided by this factor for the same purpose, the normalization. I have chosen line width as 2 and gave all the lines black color, and I have used the legend as n is equals to 1, 2, 3, and 4. Give the x-axis label, y-axis label, give the title, and I have ended the for loop here because I have done with the eigenvalues. So now it's turn to plot the eigen eigenvectors, that is your wave function and probability density function. I have to plot both of them, right? So now my aim is to plot psi and psi square, correct? So for that I have the another loop, that is k is equals to 1 to 4. Okay, so in this loop what I did, I have defined the another variable, that is capital F. It starts with the 0, ends with the L, and in between 0 and L I have this f is equals to semicolon comma k. See, semicolon comma k here means that we have 99 columns of the eigenvectors as well, and we need only 4. So we need to extract them. So this is the command which is used to extract those values. Okay. So here semicolon is symbolizes that we don't do anything for rows, and k is the number of column which we want to extract. So if we have choose k is equals to 1, so it will be extracting first column of out of those 99. And if we choose 2, then it will take out second. For if we choose 3, it will take out third, and if we choose 4, so it will take out fourth one. So this is how it works. And same with the x, we have defined first of all 0, then L by N, and then L. I have defined this so that I can get the accurate plot. Okay, okay, and this is the F1 is equals to SCF1. This is to separate the graphic window, so that we can have the enlarged graph and we can have graphs on the another graphic window. And now I have used subplot because I want to plot them differently. I don't want to merge all these graph into a single plot. So I have used subplot so that I can divide them among different plots. So here I have just plotted it. I have given the x-axis label, y-axis label, title, legend, grid, and then in this I have plotted the psi, that is a wave function, and again in this I have plotted the psi square, that is the probability density function. So here we end our program, and now it's time to see the results. So if we talk about the results, so we had the eigenvalue for n is equals to 1 is this much, for n is equals to 2 is this, n is equals to 3 this, n is equals to 4 this. So here now you are reading this warning transposing row vector x to get the compatible dimension. See, uh, we have if we have the issue of the rows and column, like if we are plotting rows on x-axis and if we are giving columns for y-axis or vice versa, so it gives us this type of warning. So this doesn't mean your program has something wrong. This is just a warning, so you can ignore it. Now we have graph for energy eigenvalues for n is equals to 1, 2, 3, 4. And here the legend symbolizes that what each color means. That is this for n is equals to 4. This is for n is equals to 3. This is for n is equals to 2. And this one for n is equals to 1. And now the graph for wave function and probability wave function. So the plot for wave function is this is for n is equals to 1, 2, 3, 4. And these are the plots for the probability density function. And this is the summary table uh, to check which value of n give us the least error. Like this is to check that if we are heading towards the convergence or not. So this is the whole program. This is the explanation about whole program. So I hope you have understood it.